Hello and welcome to Agents of Tech, our brand new science and technology podcast. I'm your host, Autria Godfrey.
And I'm Stephen Horn.
Together, we want to explore the cutting-edge technology shaping our world today, from big data and quantum computing to AI and robotics. Agents of Tech delves into the science and applications of these technologies and the ways in which they can meet some of society's biggest challenges, addressing issues like inequality, climate change, and improving healthcare.
Each episode features in-depth interviews with leading experts in the field, discussing the latest developments and their potential to improve our lives. Whether you're a tech enthusiast or just curious about the future, Agents of Tech is for anyone interested in the intersection of technology and society and where this might lead us.
Okay, Stephen, so you were just back from the American Physical Society March meeting in Las Vegas, Nevada. How was that?
It was awesome, Autria. It's an incredible event, the largest physics conference in the world, a diverse international community of over 10,000 scientists coming together to celebrate the frontiers of physics, looking at new research and hopefully nurturing the next generation.
Yes, no kidding. So just who all have you been speaking with? You've been busy.
You know me, Autria. Who haven't I been speaking with? I had the pleasure of meeting Robert Rosner. He's the 2023 APS President, and he's an astrophysicist. He's also someone passionate about the role of physics in society and, crucially, in public policy. He's got some very interesting insights into energy and climate change and how scientists can work with governments and other stakeholders to develop solutions to our energy crisis. But first, I asked him about a question dear to his heart, one he spent his career exploring. What are the origins of cosmic magnetic fields?
We know that planets have magnetic fields. We know that stars have magnetic fields. We know that galaxies have magnetic fields. You can find magnetic fields anywhere where you look in the universe. And the obvious question is, where are they from? Did they originate before the time when the universe became transparent or afterwards? How does it happen in the stars? How does it happen in planets? Theorists have developed ideas about how this might happen. Probably the first key paper was by a colleague of mine who's since passed away, Eugene Parker, who had the first concrete suggestion of how, for example, the sun might generate its magnetic field. Now, since then, there have been three different questions that have come up. One of them is, where do the seed magnetic fields come from? The starting bits. And there is an answer to that theorists have. It's called the Biermann battery mechanism. We know that we're surrounded by turbulent fluids, turbulent conducting fluids, let's call them plasmas. You stick a magnetic field in, what happens? And theorists have developed the idea that turbulence in a conducting fluid can actually amplify these seed magnetic fields. And then finally is the question of how these large-scale fields that, for example, the sun has, and the paper by Gene Parker that I mentioned before was the first one that actually came to basically explain that. That's just all theory. Right. What about experiment? So it turns out one of the remarkable things of the last decade or so is that it's been possible to do experiments that validate the idea of the Biermann battery mechanism to generate seed fields. And it's been possible to do experiments that then demonstrate that turbulent plasmas, in fact, exponentially amplify these seed fields. And these experiments have been done on some brand new experimental facilities. The National Ignition Facility at Lawrence Livermore, for example, the Laser Energetic Laboratory at Rochester. So we have a pretty good understanding of what happens to the seeds, how they get amplified. The question is, what about this order? And it turns out Gene Parker's idea wasn't the only one. It's not the only one of doing it. And so there's a bit of controversy of which way it's done. And in order to decide, there's nothing like experiment. And the crucial question is, will we figure out how to do an experiment? So where my thinking is going is, thinking about how one might construct an experiment to validate this idea, how order can come out of chaos, like it does in the sun, like it does in the planets, like it does in the galaxy.
It's very interesting, isn't it? Because you're talking about new facilities that enable you to be able to conduct experiments
Absolutely.
that you might not have been able to do
Right.
before. And that must be very exciting for a physicist.
It's hugely exciting, and also what's particularly interesting is it's hugely accidental, because the facilities I was just talking about were not built, they were not paid for with the idea of entertaining people like Bob Rosner to do his science. They were actually conducted for a totally different purpose. They were constructed for the Nuclear Stockpile Stewardship Program by the Department of Energy. So it turns out those facilities have what is sometimes called an open science program, so where you can do unclassified experiments. And my colleagues, for example, at the University of Chicago, in collaboration with folks at Oxford, for example, at Rochester, were able to do the experiments that I talked about before.
I know one of the other areas that you're very much engaged with is energy, isn't it? Talk us through that.
So I became interested in energy matters when I was at Argonne. I was the chief scientist and director there, and I spent a fair amount of time in Washington, D.C. And what I discovered, when it comes to technical matters, including energy, there are sensible things said, but also a lot of things said that are, I would say, are, let's call it hot air. And so I got interested in this question of whether or not we can do more as scientists to become part of the conversation. So at the University of Chicago, it led me to, with a partner, an economist named Bob Doppel, to create an energy policy institute called EPIC, which had this unique feature of a physicist and an economist actually spending time together, perhaps arguing some of the time, but at least enjoying each other's conversation and helping each other understand what's going on. And I think one of the things that I realized is that that if you think about the energy transition that we're in right now, there is a technical roadmap, which is like all technical roadmaps. I think we physicists, our colleagues in chemistry and engineering, we know how to do this. But then there's also a public policy roadmap. And that, in my view, is where the problem is. In order to accomplish what we want to do on the technical side, we need to have a clear understanding of what needs to be done on the policy side. So let me give you a concrete example. In order to deal with the new generation capabilities of renewables, wind and solar, which are becoming increasingly dominant, we know we have to restructure our electric grid. Well, in the United States, that's a difficult thing to do because the federal agency that's responsible for the grid, FERC, is unfortunately not empowered to really do this easily. And so there's a roadblock here that's legislative in nature, and one of the consequences is you get into these partisan arguments that basically just delay the whole business. And so, okay, we may be generating lots of electricity by renewables, but we don't have a very good way of now dispatching it in an efficient way. So what I see is we have to figure out a way, perhaps scientists can help in turning the conversation on the policy side away from partisan matters and doing what we've done in other areas. For example, in space matters. I think both parties, Republicans and Democrats, were together in their vision of what should happen in space. And so NASA has always been a fairly apolitical kind of agency. During the Eisenhower administration, when we built out our national network of highways, again, that was pretty much a nonpartisan issue.
Right.
And we need to find that also in the energy field, and we're not there yet.
An outsider might say, perhaps not hugely constructively, that stakes are very high.
Yes, they are.
I mean, one could argue that the future of our planet is at stake here. The stakes are very high, and the consensus that you're hoping for seems further away than ever.
Right. Yes, it's true. It's driven by many factors, some economic. There's no question that it's expensive to change large systems. So people with vested interests are challenging to move. We see this, for example, in getting rid of coal. We have a state, West Virginia, where the coal industry is a mainstay of the economy, and we have to figure out a way of helping them survive this transition. I see this really as trying to find a way of a win-win, where, for example, the folks in West Virginia can understand that they will be helped through this transition, that we're not just throwing them to the wolves. And so those kinds of things have to happen.
So how does public policy evolve? I know you're very interested in public policy. So how does public policy evolve to tackle, these thorny issues?
Very, very slowly. Unfortunately, I mean, I think, as physicists, we're sort of used to, we've made a decision, this is what we're going to do, let's do it. That's not quite how it works. And so what we're running into here is, of course, a problem that science has more and more today, which is the skepticism that many in the public have towards science. Just because I or my colleagues say this should be done doesn't mean that people will applaud and say, yay, verily, we should do this. Part of the problem is our language. When I talk about a topic with my colleagues, I use certain words, vocabulary, that I think can easily be misunderstood by others who are not steeped in science culture. So, for example, when I say, I think I'm uncertain about this, I recall telling this to one of my uncles, and talking about some energy problem, and I said, well, we're not quite certain about this. His response was, well, you mean you don't know what you're talking about? I said, no. So we have to explain, when we say we're uncertain, we have to explain what that means. That's the point number one. And point number two is, as scientists, we're used to changing our mind when we get more evidence. That can be also misunderstood because it could be said that, well, your previous opinion, you were just lying to us, you're just making it up. And I think the idea that we respond to changes in evidence is something that is not a trivial matter to explain, and has to be done the right way. And that has to do now with language, that I don't think anybody, scientists or not, likes to be talked down to.
You make a lot of really interesting points, but you talked there about the way that scientists might work, about reaching a consensus and taking something forward. But you also talk about the sort of trust deficit that there is, and one almost feels like that the scientists maybe work in a different way to those people who don't believe or have that trust in them. So what do scientists, not need to do, what can scientists do to help in this area?
I think the APS has programs in this regard. The theme really is trust science, and the question, how do you do that? And I think the way that's done is basically to have, we're part of a social milieu. We have neighbors.
Right.
All of us have neighbors. And there's nothing wrong with us talking to our neighbors about how we feel about issues that touch on science, what science matters. And these conversations are not conversations where I'm lecturing somebody, because that's the last thing that needs to be done, or we just talk about something, where we listen to the concerns of the people that are our neighbors, and we respond to them in a way that isn't a matter of just us lecturing them, but basically trying to explain.
I guess my final question is something you've touched on before, which is the future of your profession. And how kind of encouraged are you by young people coming through, and what do we need to do to help?
There are two answers to that. So the first one has to do with the question of, what about physics itself as a discipline? My sense is that we're really on the threshold of an entirely new era of physical sciences. In part, that's driven by the fact that we have new ways of looking at data. I think the advances that have been made by our ability to gather enormous amounts of data, to process it, to store it, and to process it, to use, some people will call it AI, but I would prefer to call it machine learning capabilities, to search for regularities, to improve our ability to optimize, to do things like, for example, invent new ways of synthesizing materials that are purpose designed. All these kinds of things. We're right on the threshold of this major transition. And it couldn't come at a better time because we're also in this transition in our energy world. And so many of the kinds of things that need to be done, for example, new materials, new processes, figuring out, for example, how to build buildings that involve methods that don't emit so much carbon into the atmosphere. All these things all go hand in hand. And so I think first of all, there's a lot to do, a lot of new things to do. And what's particularly interesting, this is really basic research that's driven by needs. And so sometimes our students, I've had students who've come to me and in a sense exhibited some regrets that they're doing some science and the science is ignoring the rest of the world. And actually physics is moving in a direction where it's not like that, where what we do matters for the rest of the world. So it's inspiring. So what I'm saying is that actually to be young at this point in time is just a great time to get into this field. And I think it's pretty clear that we're limiting ourselves to the extent that we don't invite everybody who can do this into the fold. And so I'm a huge proponent of going after folks who traditionally might not be thinking about physics, people that are definitely underrepresented in our discipline. All that's required is to have the enthusiasm and the smarts, and you can become a physicist and have a great time. I've certainly had a great time being a physicist. Why can't others?
So what I'm hearing is that we are on the threshold of a great new era in physical science and materials research. In fact, physics has never mattered more. It's an exciting time to be a young scientist, and we need scientists from diverse backgrounds.
You're absolutely right, Autria. Is one of the drivers of this new era in physics is, of course, quantum computing. And it's a hot topic at APS as ever. Someone leading in this field is Monika Adelsberger of Ludwig Maximilian University of Munich. She works in quantum simulation. She's trying to understand quantum systems atom by atom. Now, Monika, I would be a rich man if I had $1 for every time somebody said quantum to me at this particular conference. But can you tell me what the difference is between a quantum simulator and a classic simulator?
The basic answer would be, of course, that it's made of quantum systems, right, that actually interact with each other in a quantum mechanical way. Now, the question may be, okay, what's that? And if you think about a classical simulator or maybe even a classical computer, then that's easy to understand. So we have something to calculate zeros and ones, we have bit strings, and we all know how that works. Now, if you look at a quantum system, that's much more challenging because they are not only 1 and 0, there's a lot in between. And because that's so hard to compute and capture classically, the idea is now to build a quantum system that behaves in a proper way. The challenge is you actually have to be able to control these individual quantum systems to a very high degree.
How does that work with a simulator?
Right, so the simulator does exactly that. So the basic idea is we do an analog quantum simulation. So you have some problem that is hard to compute classically that you would like to study.
Okay.
So now that can be very complex, has many degrees of freedom, could be a material, there's all sorts of things that are challenging to capture. And now theoretically we write down a simplified model which has few microscopic parameters, few degrees of freedom that we would like to solve. But even that simple model is typically not solvable classically. So that's challenging. So what we now do is try to build the simple model in the lab. So we go ahead, we take these few degrees of freedom that we need, we recreate it in the lab where we control it very well, and then we probe its properties. And then the idea would be to have a feedback to the theory so that we can learn something from the quantum simulation that we then give back to the theorists in order to have better approximations, maybe understand, well, are these all degrees of freedom? Do we need to add more? And then there would be like this feedback loop between these systems.
How much more powerful do you think quantum simulation will be? I know it's early days and you've got a lot of things you're trying to work through, but what's your hope?
So my hope would be that during the next few years, we actually find efficient ways to verify and benchmark our experiments to begin with, because that's the challenge. Right now, we have very well-controlled quantum systems, and we can compare them to theory in the regimes where we can actually describe it completely. But we want to go beyond. And going beyond means that we need to find some way, either by cross-platform verification or by other benchmarking techniques, to actually build trust in our simulations, that we can say, okay, we do run this computation and we actually believe the result that comes out of it.
What got you so interested in this field?
So for me personally, it's just fascinating to see all of this, all of the beautiful physics of quantum mechanics to unfold in the lab, so that you can actually really see that the systems that you build behave quantum mechanically. You can control them, even manipulate them, and really, if you wish, play with quantum mechanics in the lab. And that's what really got me excited about this. And because they are quantum systems that we control in the lab, they are broadly applicable to other research areas. So you can use them and actually learn new physics. Like, they can be applied to different model Hamiltonians that you can study. And so there's always room for learning more on our end and see what we can use them for.
Describe for me some of the breakthroughs you've had in your lab.
I think the most important one was really on the engineering side. So one question for quantum simulators is, what can we apply them for? Like, what model systems can we actually look at? And we have worked for a number of years now on implementing topological lattice models, which is something that does not just naturally occur if you prepare the atoms in the lattice. And this required the development of new techniques, new experimental methods in order to get there. And I think we are quite proud of that we have developed some of these techniques which are now used in many different labs around the world. So I think that's one of the biggest contributions at this point that we could make.
A lot of the interviews we've done today, people have been talking about new breakthroughs. They've been talking about it's a very exciting time to be in physics, and with quantum, we've got a lot of different techniques with data now, and we've got a lot of ways of analyzing data, and that we're on the cusp of something big. Do you think that's right?
Well, I think it's definitely exciting to find out within the next few years how well these systems work and how far we can push them in order to develop new technologies and learn new physics. So I think we are at the brink of finding that out, which makes these days very, very exciting.
So Monica has developed quantum techniques that are now being used in labs all across the world, pioneering work in the true sense. But what I really take away from this is that we are on the cusp of a quantum revolution that's going to change the world. To coin a phrase, quantum computing will change everything, everywhere, all at once.
Oh, very good, Autria. Yes, the race is on to develop quantum computing, and as we're hearing at APS in Las Vegas, Nevada, the stakes could not be higher. A quantum computer promises to open new frontiers in mathematics, enable discoveries about space and time, address the problems of climate change and food scarcity.
It's a topic that we will return to again and again in the course of the Agents of Tech podcast. Next time, we're speaking to Albert Laszlo Barabasi, a network scientist whose work includes revealing the structure of the brain to treating diseases using network medicine to how networks affect the economy and even climate change.
And we'll hear from Brad Marston about how theoretical and computational physicists can help us better understand quantum matter. So until then, it's goodbye.
Goodbye.